Hi, welcome to part 3 of the BGA Rework primer, where we're going to be talking about device placement. When we're talking about the device placement, we want to make sure that the device, after being removed, or the rework area device is removed, and the site is dressed, that placement is done accurately and properly. The third part of our process in this series on the BGA Rework a Primer series is the placement process. And the objective here is to, as accurately as possible, place the BGA so that the acceptance criteria from the client or that we're working towards can be met. Again, when we do the placement process, we don't want to destroy nearby components or the laminate. One of the methods that has really brought to light, specifically for the NPI process or for the repair process, are the stay-in-place stencils. In this technique, a stencil is placed onto the board that's already been prepped and cleaned and inspected. And we can see that in this photograph. And then, after being placed, the device is tactily fit inside the apertures of the stencil. So let's see what that process looks like. So for 1.27 or 1.0 pitch stencils, one can do this part of the process without any magnification. If we have smaller pitch devices like 0.8 or 0.5, this part of the process definitely needs to be done with some kind of magnification. So starting at adjacent edges and then working your way to the opposite corner is how we suggest to do that. You have to apply tape over the edges of the stencil so that when you roll the solder paste through, that it's not leaving remnant solder paste near the edges of the device. We have to make sure we get any remnant solder off of the surface so that we don't leave solder fines or balls behind after the reflow process. And also we don't want nearby shorting to occur. A simple Kim wipe, static-free Kim wipe, will dab off the remainder of the solder paste. And here's where we can just tactically fit and feel those balls sliding down into the apertures, and there we have the device placed. So the stay-in-place stencil method is a quick, easy way to place BGA devices for a placement part of the process. We can also use higher-end rework systems as shown here, and there we have a time temperature profile characteristic curve that we're trying to program into the machine such that it emulates the original assembly process. It also usually has a split vision system in it to align the balls to the pads accurately, and this will ensure proper placement. Another approach that can be used for rework process is flux paste dipping. Now the general camps, if you will, of BGA placement are flux only attachment, and that is the majority of the market. Thereby we have a device, a reballed device, replacement device, that gets put into flux paste that is applied to the board. That again is about 80% of the placements, at least in the United States, with the remainder being cases whereby solder paste is printed on the patterns, on the pads themselves, on the board, and the BGA placed into that solder paste. In this particular case, this is an adjunct of the flux method, whereby a device is placed into a little fixture. So in this case, we have a fixture plate that has a well that's about 60% of the height of the balls on this particular device, and it's dipped until it bottoms out into this plate, thereby coating the balls up to about 60% of their diameter in flux paste. Then it goes from this flux paste dipping operation and gets applied to the board. The advantage of this particular approach is that you can have a faster time of cleanup, as paste flux is not everywhere on the board, rather only on the balls. Then we have a component printing stencil, and a very similar approach is used, only here we're going to be using solder paste. In this case, the device is flipped with the balls side down. This particular example is a QFP, but nonetheless, we would have apertures, a little stencil on this side of the fixture. The device would get placed down into those apertures. The device would be flipped over and paste would be applied. That would be, again, about 60% or so of the diameter of the ball, thereby putting solder paste onto the bottom of the ball. Again, here it's a controlled method of applying solder paste to the ball. When we are paste printing onto the device area, the common approach is to use a metal stencil as indicated here on the photo. The reason this particular photo is perpendicular, or taken perpendicular, is we have a special kind of miniature stencil. These miniature stencils are made out of stainless steel. The apertures are cut in them just like regular SMT stencils. But in this case, we have a little lip on the miniature stencil, and we also have adhesive on the bottom side that allows it not to slide around during the paste printing process. However, if we had a regular stainless steel stencil in there, what we would do is we would align that stencil. We'd have to fix it in position, ensure that it was coplanar, and roll the solder paste through. Again, we get one shot at this, and so we have to make sure that we roll the solder paste through each one of those apertures. This particular process, though it emulates the original manufacturing process exactly and has a better first pass yield than flux paste only attachment, adds time and adds for tooling cost for this particular operation. The level of skill and dexterity and experience from the operator side is also greater. In addition, there are some tricks or some gotchas in this particular process, and that is there's sometimes a lack of coplanarity between the stencil and the board, and that can cause solder paste smearing. Also, the stencil can move around during the printing process. Many times we have bypass caps and other resistors around the BGAs, and that makes it difficult to fit these devices in. Lastly, when we remove the device, unless we perfectly lift it up, which is impossible to do with these metal stencils, perfectly perpendicular to the board without smearing, we're going to have to carefully lift it up and hope that we haven't smeared the paste print pattern. Otherwise, we have to start over. These particular metal stencils have been overcome by way of these flex stencils. They are plastic stencils with an adhesive backing. This particular one we're looking at here is of a leaded device, but the same principle applies. In this particular case, they can fit into tight areas, thereby overcoming one of the weaknesses of the metal stencil approach. The adhesive on the backing also prevents this sliding around that I described on the metal stencil. In addition, you get multiple chances to fill those apertures as the stencil is held in place. That ensures that we have proper solder paste volume shoved into those apertures. So coplanarity is ensured, multiple swipes are ensured, and we can fit it into tight areas. And this is what the print quality looks like. This is on a BGA pattern, so it's very consistent solder paste volume. Another approach we can use is we can use a paste dispensing system. This is a particular high-end system pictured here where we have an XY gantry system. It uses a teach pendant, or uses CAD data to manipulate the position of the paste being dispensed, and also has a heat control portion to ensure the rheology of the solder paste in that squeegee is consistent. So it's a slow process, but we can apply solder paste to select areas, i.e. those pads, and have a good print pattern, if you will, on the board. However, we have to get somebody to program it, and it does take long, and like anything like this, whether it's an adhesive system or whether it's a paste dispensing system, eventually it's going to clog. When we talk about aligning the BGA, we also have to be cognizant of the ref designator and have to tell us, too, what the orientation of the part is. So in this particular case, we have a slice of the interposer that the BGA package is sitting on. So that's patterned onto the silk screen. We also have a pin 1 designation. That's where the ref designator goes. Sometimes we have the package that's beveled as well. So we have to make sure that we align it properly. Then on these higher end systems, as I previously described, we will have a split vision system where we're looking at the balls at the same time aligning those to the pads on the board. So we have a micro adjustment that could be manual, could be automated. And you're essentially moving the board around so that it aligns with the balls so they end up hitting the pad. So that's the split vision system for proper alignment. So in this session we talked about the different methods for aligning the product. We talked about the stay in place stencil method. We talked about flux dipping as well as different fixturing approaches. And we also talked about dispensing. So join us next week as we talk about the BGA reflow process.